Good late morning, everybody. All right, announcements. So test number 4. Yes, test number 4 was returned yesterday. So as always, if you have any questions about it, please do let me know. Test number 5 begins on Friday. So yeah, that's coming. Covers material in it directly covers material in 3.5 and 1.8. Obviously, indirectly, I'm sure it'll cover earlier stuff. So that is coming up. Obviously, that's the last term test, considering next week is the final day of class. And I'm say, and so obviously with the continuation of strikey type stuff, the VW deadline has been pushed back to December 10th. I can't guarantee that everybody's tests will be marked by the 10th. Obviously, that is certainly the hope, but I can't make that guarantee. That being said, you have a midterm 4-term test to base anybody who's still thinking about whether or not to VW. You have plenty of stuff to base that information on. And yeah, there is a booklet of old final exams that are in the bookstore. They are probably, in terms of material, are pretty on in terms of where we are for the final. I know it's been a bit iffy to try and use them for the term tests because our structure of term tests is not exactly the same, but when it comes to the midterm and the final, it is pretty decent. All right, I think that's everything I have in terms of announcements. Does anybody have any questions about any of that? No. So our booklet of old midterms and final exams is something that the department sells to fund some of our undergraduate scholarships. So it's not something that I can just upload. All right. If you have any more questions, feel free to fire them off. If not, there's 3 questions on your screen, so feel free to get started with that. How the final will be formatted, the same as the term test and final exam, or in midterm, just longer. So the midterm was 50 minutes. The final exam is 2 hours, so it'll be roughly twice as long, maybe slightly more than twice as long, but in terms of like style of questions, types of questions, stuff like that, it shouldn't really be any different than what you guys have been doing all term long. But we haven't even started making the final exam, so I'll have more information about that as we go along. Not exactly sure when the final exam period starts. Is it? Okay. 3 weeks. No. I mean, I don't even know when our exam is, so. On the 16th? Okay. You say so. You didn't hear it from me. Oh, I asked myself the same questions. I wish I had more control over stuff like that. Alrighty, so we have our linear operator again. So just in terms of where we are going with all this transformation stuff, the entire ideas of what we're dealing with are in 4.9 anyway, is we have a bunch of transformations. They're going to all be linear. We've already talked about how to show that they're linear. That they're going to represent some kind of geometric idea, and then we're going to talk about how to find the components and or find the standard matrix so we can handle it algebraically. So that's the whole purpose of this. So we talked about the zero transformation. We talked about the identity transformation. Operator technically. We've talked about contraction and dilation operators that change how big the matrix is, but not the direction. Or sorry, vector, but not the direction. So now we're going to start talking about reflections, projections, rotations, stuff like that. So we'll start off here with the reflections. So let's say we had a vector v right here, and we want to reflect it about the y-axis. So we're reflecting it about the y-axis, so instead of shooting off to the right, we can shoot it off to the left. So we've already talked about two ways of dealing with the finding that standard matrix. We can find the components first and then just take the coefficient matrix, or we can do other ways. So obviously we want to find the components if that's easy enough to do. We resort to the other way when that's not quite so easy. So v is equal to xy. If we're sticking in R2, what is t of v going to equal if we reflect over the y-axis? Is there a comma there? Yeah, so that's negative x and y. In other words, the x becomes the opposite sign. If it was positive, it becomes negative. If it was negative, it becomes positive. So in this case here, now you don't need to write this. This is just me being extra educational. So this would say W1 is equal to negative 1x plus 0y, and W2 is equal to 0x plus 1y. So what does that tell us? This part you would. What does that tell us about the standard matrix? What's our standard matrix equal to? So that'd be negative 1, 0, 0, 1. So in other words, this negative 1 indicates the fact that the x got replaced with its negative. The fact that this is just 0, 1, specifically the 1, indicates the fact that the y stayed exactly the same in our standard matrix. All right, so any questions about reflecting along the y-axis? And the x-axis is certainly similar. All right, it gets a bit more exciting if we start to reflect along other lines. So here we have y equals x. And we have our vector here again, v, which is going to be xy. So what is that going to do if we find the reflection about y equals x? Yeah. So this relates to inverse functions. So if you remember back, again, this is a high school math thing, but if you find an inverse function reflecting about y equals x, just switches the order of x and y. So in other words, t of v is over here, and t of v is going to be equal to y x. So where we had an x, it becomes a y. Where we had a y, it becomes an x. I mean, if the original vector was in the third quadrant, then its reflection would stay in the third quadrant as well. So if, let's say, xy was here, which is certainly possible, then t of v would also be in the third quadrant. So what would a reflection across the x-axis do? Actually, let's finish this example first, and then I'll come back to the x-axis thing. So T of v is equal to yx, so what would the standard matrix of T be equal to? So this y would say 0x plus 1y. This x would say 1x plus 0y. Get 0, 1, 1, 0. And it gets a bit more complicated if we reflect along different lines. You'd have to mess around a bit with the slopes and stuff like that, but either way, we could get a standard matrix, and these reflections are always linear transformations as well. All right, any questions about the reflecting about y equals x? All right, so if we were reflecting about the x-axis, what would happen? We had, let's say, xy. If we were reflecting about the x-axis, what would happen? Yeah, we'd go down here. Again, the x would stay the same, and the y would become its negative. So if we're reflecting about the y-axis, x becomes negative. If we're reflecting upon the x-axis, y becomes negative. Or, I mean, I guess I shouldn't say negative. It becomes the opposite sign, because if it was negative, it becomes positive. I mean, the final answer will depend on the original vector, but the function itself doesn't. So for the x-axis, t of xy becomes x negative y. That's the function. The function itself doesn't depend upon the specific vector. Obviously, when you plug in different vectors, you get different answers. But the function itself is the y becomes negative. So how did we get 0, 1, 1, 0? Okay. So here's W1, and here's W2. So W1, what's the coefficient of x in? So if we just rewrote the y as, let's say, a11x plus a12y as its coefficients, what's the coefficient of x? That would be 0. What's the coefficient of y? 1. Similarly, W2 is 1x plus 0y. In other words, 0, 1 gives us this in our coefficient matrix. 1, 0 gives us the second row in our coefficient matrix. Yeah, it's pretty much, and not just for the y-axis, but any of these things. If we have the coefficients, like if we have the components of T of v, we're just getting them by picking off the components of the x, the y, or if it's on R3, the x, the y, and the z, as we'll see in our next example. So that's the benefit of having the components. If you have the components, then getting the matrix is just by looking at the coefficients of those components. It's more complicated if you don't have the components, and we'll see an example of that later. Then we have other methods for finding that standard matrix, and we'll see that when we get to rotations. All right. Any other questions about the R2 reflections? Reflections on R2. So W1 is always the x coordinate of the answer, and W2 is the y coordinate of the answer. So is your question where we got T of V from, or why we got what, how we got W1 and W2? So is your question about what I'm boxing in purple or what I'm boxing in blue? So the W1 is always the first component, and the W2 is always the second component. Now, usually we don't write W1 and W2, but W1 is the first component, W2 is the second component of the answer, W3 is the third if we need a third. As for where I got the negative 1x from, it's just whatever makes it negative x. All right, so let's 3D this up so I can really look foolish in how I can draw. So here's our y, here's our z. So here we have some vector v equals to x, y, and z. And now we're going to reflect it about the xz plane. So we're not reflecting about a line anymore because that doesn't really make sense in 3 dimensions. We're going to reflect it about the xz plane. In other words, here's where my bad artistic skills are going to come into it. We're going to reflect it about kind of this plane right here, the xz plane. So what happens to xyz when we reflect it about the xz plane? Fortunately, the algebraic ideas are the same as when we reflect it along the x or y axis. What happens to the x, what happens to the y, and what happens to the z? Yeah, that's right. The y becomes negative. Now that's hard for me to demonstrate with my bad artistic skills. That's wrong. T of v equals x, y, and z. So if we're reflecting about the xz plane, then a positive y becomes a negative y on the other side, and vice versa. In other words, the y becomes the opposite sign. So the nice thing about reflections, at least reflections about what we call the coordinate planes, x, y, x, z, or the y, z plane, is that it just takes one of the components and makes it negative. In this case, that's the y. Right, so any questions about the components before we jump again to the standard matrix? Exactly. Exactly. If we're reflecting about the YZ plane right here, then we would take what looks like a negative x and bumps it to being a positive x or vice versa. Same thing for the xy plane. If we were above the xy plane, aka z is positive, when we reflected about the xy plane, then the z would become negative again, or the other way around. Right, so that's the components. Do you have to write it every time? Depends on what the question asks you to do. Yeah, that's exactly what it is. So for the xy plane, the z becomes negative. It's the one that wasn't there. For the xz, y became negative. For yz, x became negative. It's the one that's not there. And that's no different than R2. In R2, for the x-axis, the y became negative. For the y-axis, the x became negative. So it's not really some different thing for 3 dimensions. It kind of follows the same ideas. Yeah. So for our standard matrix, x is 1x plus 0y plus 0z. So our coefficient for x is just 1, 0, 0. For negative y, the coefficient of x, y, and z are 0, negative 1, and 0. And for the z, the coefficients, it's 0x plus 0y plus 1z. So our coefficients are 0, 0, 1. So yeah, the question about do we have to write the standard matrix every time? The answer is depends if the question asks you to write the standard matrix every single time. And my questions did. All right, any questions about reflections? Basically, these are how the reflections tend to go. Right? So that's reflections. Let's talk about some projections. So very similar questions, some axes, some lines, some three-dimensional stuff, but instead of being a reflection, now we're going to do a projection. So I'll give you a few minutes to give that a try. What was the standard matrix of the 1 over the x-axis? The y would become negative. So it would be 1, 0 because the x stayed the same, and 0, negative 1 because the y became its negative. Again, I don't want this to turn into memorize 100 different things. It's really the ideas that's going on. If you're dealing with reflecting about the x-axis, the y becomes negative, and we can get the standard matrix from there. Not that I'm going to stop anyone from memorizing the 20 or 30 different standard matrices for all these different possibilities, but it's really the ideas that I'm trying to focus on. All right, well, we've seen projections before. We did projections in section 3.3, 3.2 or 3.3, I can't really remember. And that's exactly what we're talking about right here. So if we had a vector, again, let's start with the geometry. If we had a vector, v is xy, geometrically speaking, what does the projection into the x-axis going to do to this vector? Yeah. We'll just drop this perpendicular onto the x-axis, and then the projection is finding that vector we're left with. In other words, the y becomes 0, and what happens to the x? Wrote the wrong one. The y becomes 0, and what happens to the x? Stays exactly the same. In other words, t of xy becomes x0. So that's our projection into the x-axis. The question didn't ask for it, but you could probably guess what projecting into the y-axis is going to do. If projecting into the x-axis makes the y equal to 0, what's projecting into the y-axis going to do? It's going to make x being equal to 0. Again, if it's not the axes, as we're going to see in our second example, it becomes a bit more complicated if we're not talking about one of our axes, but that's for our next example. All right, so any questions about what the projection does geometrically before we start talking about the algebra and the matrix? Right. But there's nothing here that isn't what we would have talked about with vectors, and we'll see that in our next example. All right, so what is the standard matrix? If the first component stays x and the second component becomes 0, again, I'm going to go overkill a little bit. W1 equals to something x plus something y. W2 equals something x plus something y. So what's the first somethings for the W1? Again, this is really overkill and unnecessary, but if it helps for understanding, that's the purpose. Yeah, so W1, the first component, is 1x plus 0y. As for W2, in our matrix transformation, 0x plus 0y. In other words, it's 1, 0, 0, 0. There we go. And there's our standard matrix for a projection about the x-axis. Basically, the y went from 1 to 0. Right. And y-axis would be nearly identical, except the roles of x and y would be swapped. So any questions about an x-axis projection in 2 dimensions? All right, so for y equals x, it becomes a little bit more exciting. And honestly, how we're going to handle y equals x is the same way we could handle projecting along to any line. Really is not going to make any difference what we're about to do. So let's say I had xy right here, and we're projecting onto the line y equals x. So again, let's start with the geometry. What are we doing to V in order to get the projection onto the line y equals x? So we're going to get this perpendicular onto the line y equals x. In other words, t of v that we're looking for is this vector right here. Here's t of v. There's our projection onto the line y equals x. So geometrically speaking, that's exactly what we're doing. We've already seen in chapter 3 some applications of doing that. So the question then becomes, what are the components? How can we find the components of t of v? And we've done it before. This is not something that's new. Well, xx is certainly going to be the vector's direction, but it might not be the length. And in fact, it probably won't be the length because x is over here. And as we can see here, it doesn't really seem like the x is staying the same. The x is not staying the same. The y is going to have to equal x, but the x itself is going to change. So it's going to be some multiple of that. But we've done all this before. This is finding a projection. We've done projections before. Right. That's the projection of something onto something else. Yeah. It's exactly having something to do with our projection formula. Of course, we projected one vector onto another vector, so we certainly have the vector v, but we've never projected a vector onto a line. Our formula is projecting a vector onto a vector, not a vector onto a line. So what can we do about the fact that we're as given, we're trying to project onto the line y equals x, but we need a vector. A line doesn't do the job. We need a vector. And norms deal with lengths. We don't really care about the length. So if we're projecting onto the line y equals x, then that's the same thing as projecting onto what vector? My question is, what vector is parallel to the line y equals x? What vector is parallel to the line y equals x? And there's lots of them. I'm not asking for all of them. We just need one. That's not a vector. I mean, x could be a lot of things. K can be I just want one. Just want one. 2, 2 sounds good. 2, 2 is a vector parallel to this line. So is 1, 1. Somebody mentioned 1, 1 earlier in the chat. That's correct as well. So is 3, 3. So we can project v onto a vector parallel to the line. So the only thing that makes this different than what we did in section 3.3 is we're given a line and we want a vector parallel to that. But we did that in 3.4. Given a line, what's a vector parallel to it? So that's not new either. Slightly different context, maybe. But we can project v onto 2, 2. And, I mean, like I said, 2, 2 is not some special, it can only be this thing. 1, 1 would do the job. 5, 5 would do the job. Any vector parallel to y is equal to x. All right, so any questions about how we got the vector parallel to this line? All right, now we just let the formula take over. So T of v is equal to, what's that, v dotted with 2, 2. 1, 1 might have been easier, but I saw 2, 2, technically second. And there we go. And now we just have our projection formula from back in chapter 3. V is, what's that, xy. And now it's just some calculations. But it's all the same type of stuff we did back with projections back in I think it was 3.3. So 2x plus 2y for our dot product. That's going to be what, the square root squared of 2 squared plus 2 squared times 2, 2. What's that? 2x plus 2y over 8 times 2, 2, which is what? 4x plus 4y over 8. 4x plus 4y over 8. Obviously, 4 over 8 is just a half, so x over 2 plus y over 2, x over 2 plus y over 2. So if it's the x-axis of projection's very easy. If it's the y-axis of projection's very easy. It's obviously more complicated if we're projecting onto a different line. But really, it's just the projection stuff from chapter 3. All right. So any questions about how we got our projection formula or the annoying calculations that came out of our projection formula? All right, and I will note that If we use, let's say, 1, 1, a lot of these numbers would change along the way. That being said, and feel free to try it, if we did this with 1, 1 instead of 2, 2, you will end up at the exact same place at the end. All the constants would cancel out along the way. All right. So any questions about how we found our components? All right. So what's our standard matrix? I'll give you that it's a 2 by 2. What's our standard matrix for this linear operator? Nope. Half right. Pun intended. Yeah, so what's the coefficient of x and y here? So our first row would be a half and a half. And our second row would also be 1 half, 1 half. Basically, all the coefficients are a half. And since we were projecting onto y equals x, the fact that our y component in our answer and our x component of our answer are the same should be very much expected, considering we were projecting onto the line y equals x. I know this isn't the question, but I'm changing the question now. What if we projected onto y equals 2x? What if we were projecting onto y equals 2x? What about this process would change? What about this process would change if we were projecting onto y equals 2x? So the line changes, which in turn changes what? Right, the parallel vector. What vector would be parallel to y equals 2x? So what vector is parallel to y equals 2x? Yeah, 1, 2, for example. And then everything after that would be using the vector 1, 2 instead of the vector 2, 2. But every step afterwards, with obviously some calculations are slightly different, but everything else would stay the same. So if we're reflecting along any other line, it doesn't change anything. The steps would stay the same even if the vector 2, 2 became some other vector, if it came from some other line. So this process is repeatable for any single line. All right, any questions about our 2-dimensional projections before we do a 3-dimensional one? All right, so xy plane. So now this is an operator on R3. What happens if we take a vector in 3 dimensions? And here's my poor drawing again. So let's say we had x, y, z, and we projected it down into the xy plane. There's v, here's t of v. Now that's a reflection, not a projection. X, y, negative z would be the correct reflection. But the difference here is we're not going to the opposite side. We're stopping when we hit the xy plane. It's still perpendicular, but we're stopping when we hit the xy plane. In other words, z's going to be equal to 0. So similar to reflections, when we're talking about the coordinate planes, it's usually relatively simple. When we're talking about something more complicated, then it obviously gets more complicated, but we can still manage to handle it. In other words, t of x, y, z The projection into the xy plane is just xy0. And the standard matrix is pretty much. Why is V in the YZ plane initially? Poor artistic skills. My intention was not to make it look like V was in the XYZ plane. I mean, there's already limitations on what things can look like three-dimensionally, and then you tack on some poor artistic skills. But it's not. It was not intended to be in the YZ plane. Why is Z equal to 0? Because our vector, honestly, for the exact same reason it was for up here. A reflection would make it go below. So if we did our x-axis example, a reflection would make it go below. The projection puts it on the x-axis. So projecting onto the x-axis, the answer is on the x-axis. Not on the other side, which is what a reflection would do, would be put it to the other side. A projection puts it onto the axis. So for the x-axis, the projection's on the x-axis. For y equals x, the projection was on the line y equals x. For the xy plane, the projection puts it onto the YZ plane. Or sorry, the XZ plane. In other words, it doesn't go up, it doesn't go down. The Z component is 0. As for the standard matrix, again, we start off with the identity. The x stays the same, the y stays the same, and the z becomes 0. Very similar to the x-axis, except we stuck an extra coordinate in there. All right, so that's projections. We've done reflections. Reflections, or rotations, is where things get a little bit more interesting. All right, so we're going to take rotations a little bit more at a time. So could we solve any projection as a matrix transformation? In 2 dimensions, yes. Yeah. In 2 dimensions, it would be, for sure. 3 dimensions gets a bit more complicated. So as a 2-dimensional thing, yes. As a 3-dimensional thing, honestly, even that would still be fine. You could talk about projecting x, y, z onto a vector, as long as you're projecting onto a line. It gets more complicated if you're projecting onto a plane. We couldn't just use that formula. But projecting from a vector onto a line, we could use that formula for every single time, regardless of whether it's R2 or R3. All right, I regretted doing this in my class yesterday, but I'm going to do it again anyway. So reflections. So reflections are a bit more complicated. So before we get to anything involving finding standard matrices and whatnot, why are reflections linear? And by reflections, I mean rotations. Reflections are relatively easy compared to rotations. Why are rotations easier? Or linear? I'm on fire today. All right, so we want to show an operator is linear or a transformation is linear. How do we show something's linear? Keeping in mind we don't have the standard matrix. How do we show that a transformation is linear? We got our 2 properties. So is T of u plus V equal to T of u plus T of V? And we're going to show this completely geometrically, or at least I'm hoping to give you a vague idea geometrically as to why this would be linear. All right, so let's say I'm going to draw this in 2 dimensions, but 3 dimensions. The ideas are very similar. So let's say this is U, and let's say this is V. So left-hand side, how do we add vectors together geometrically? All right, tip to tail. So right here, there's U plus V. Right. Now we're going to rotate everything. So now I'm going to rotate everything. I'll make it look like it's 90 degrees. But in general, this really doesn't matter what angle you're doing it. So here's T of U. And there's T of V. So over here, what is that vector? If I complete that parallelogram, do the whole tip to tail thing, what is that vector? That I've done in green. Intentionally the only one I've done in green. All right. Well, T of U plus V says we would take U plus V and rotate it. So is the green vector equal to U plus V rotated? Did we rotate U plus V the same as we rotated U and rotated V? Or does it, at least does it look like it? I mean, yeah, for sure. So this green vector is going to be T of U plus V. In other words, it's U plus V rotated. Someone else said it wasn't that it was T of U plus T of V. So T of U plus T of V is completing the tip to tail on T of U and T of V. So is it also equal to T of U plus T of V? Yeah. It's still the tip to tail thing. So the idea is we use this phrase, that rotations preserve addition. You don't need to remember that phrasing, but the idea is if you rotated then added the vectors together, or you added them together and then rotated, the order doesn't matter. And that's kind of the idea here. And that's why at least the first property of this is true, because if we added them together and then rotated them, or rotated them then added them together, it doesn't make a difference. We get the same thing in the end. So that's why hopefully it kind of makes sense that the first property of being linear is true. Add them together then rotate, or rotate then add them together. Geometrically speaking, we seem to end up in the exact same place. Now, I will say the textbook and maybe even my pre-lecture videos does this as a nasty trigonometry proof, which you can do, but the idea is rotating is not going to affect whether or not we add first or add later. And I'm just going to say the second property is similar. I'm not asking you to prove this. I just want to give you a vague general idea. In fact, the second property might even be easier to understand. That if you multiply a vector by 2, so here's the vector, and then make it twice as long, and then rotate it, it doesn't matter whether you doubled the length or rotated first. You end up at the same place at the end. All right, so the whole point of that is hopefully I have justified to you that it actually stays linear. Believe me, or try and prove it yourself. It's up to you. So assuming the fact that a rotation transformation is in fact linear, which can be proven, our goal here is to find that standard matrix. So let that rotation be rotating by 60 degrees counterclockwise. See if you can compute T of 1, 0 and compute T of 0, 1. If you have any questions about the why it's linear thing, feel free to let me know. Hey, did anyone get an answer at least for t of 1, 0? And again, I'm fully expecting this to be done geometrically. At least at first. Eventually we'll come up with some algebraic funness. The idea is we want to be able to do this geometrically. So geometrically speaking, how do we find t of 1, 0? How do we find t of 1, 0? Let me make it bigger. Add pi by 3 to what? So here's 1, 0. What are we adding pi by 3 to? We're rotating it. We're adding pi by 3 to the... Which component, the x or the y? So does it become 1 plus pi by 3? Yeah, we're adding it to the angle between them. We're rotating it. We're rotating it by an angle of 60 degrees, or pi by 3. We're rotating this thing. So the question becomes, if we take 1, 0, rotate it 60 degrees, what happens to the x? What happens to the y? So we want to figure out if we take the point 1, 0. There we go. If we take the point 1, 0, rotate it 60 degrees, where do we end up? And now this becomes a little bit of a fun, trig question. We're going to make ourselves a right triangle. Now somebody said we know the hypotenuse length. How do we know what is the hypotenuse length? Why is it equal to 1? I absolutely agree. Why is it equal to 1? It's the length of our vector. It's the length of our vector. If we rotate our vector, and we're just rotating it, if we're rotating our vector, are we changing its length? No. Just like a reflection, rotating it doesn't change the length of the vector. And so we know this is still equal to 1, and we know the angle, whether you use radians or whether you use degrees, is up to you, but the angle, we know that as well. So the question becomes, from the angle and the hypotenuse, can we figure out y, and can we figure out x? And hopefully the answer is yes. So how can we figure out x? So if we go cosine, again, 60 degrees or pi by 3, whichever one you like, SOHCAHTOA. Cosine is equal to what? It's equal to, in this case, x over 1. In general, it's the adjacent side over the hypotenuse. In this case, the adjacent is x, the hypotenuse is 1, and we get x is equal to, technically, 1, although we usually don't write the 1, times cosine of 60 degrees, which in this case is equal to a half. Yeah, equal to a half. All right, what about y? How do we find y? Y is the opposite side, so we use sine. So that's the opposite over the hypotenuse. That's y over 1, so y is equal to sine of 60 degrees, which is root 3 over 2. So there we go. T of 1, 0 is equal to a half root 3 over 2. All right. So any questions about how we managed to find, other than I don't want to get into an in-depth how to find sine of 60 degrees. I don't have quite enough time to get into a full trigonometry review. But in terms of where the sine and cosine functions come from here, any questions about how we're finding t of 1, 0? All right, what's the significance of t of 1, 0? Why do we care about t of 1, 0? Why is that particular vector our concern? But I mean, in terms of linear operators, linear transfer, all this linear transformation stuff, what does t of 1, 0 give us? I mean, yes, that is 1, 0, but what does t of 1, 0 give us? Yes, it's the reflection of the elementary, but what does that give us in terms of what we're eventually trying to solve for? Answer the question the way I want you. The solution, right, and what does this solution give us? What about the standard matrix? Right, it gives us the first column of our standard matrix. You'll notice that we don't have some nice formula like we did in all of our other examples. We don't have a nice formula for our components of a rotation. We're doing this to find that standard matrix. So t of 1, 0 is how we can find the first column of the standard matrix. What's the second column of the standard matrix? T of 0, 1, so let's find t of 0, 1. So here's 0, 1. Again, that has a length of 1, and we're going to rotate this thing. Try and rotate it a bit better. We're going to rotate this thing 60 degrees. Negative a half root 3 over 2 sounds good. Where are we getting that from? It's not the negative of the first. Yeah, it's not going to be the negative of the first column. It's a bit more complicated than that. Not quite. That's looking about right. Yeah, so again, we're still going to do this. Is the hypotenuse still going to be 1? Indeed it is. The hypotenuse is still going to be equal to 1. So the idea is we still want to use the hypotenuse. But in our triangle, which we'll notice 60 degrees is not part of our triangle, at least not directly. So if I look here and I look there, which of these, if any, is equal to 60 degrees? Yeah, it's there that's equal to 60 degrees. It's this one right here that's equal to 60 degrees. So it changes slightly what we're going to do, because it's that angle that's equal to 60 degrees. So, in order to solve for x, which trig function are we going to use to solve for x? Yeah, so before we used cosine to solve for x. Now we're going to use sine to solve for x. Technically, since x is negative, we're using sine of 60 degrees to solve for negative x. So again, opposite over the hypotenuse, which is negative x over 1. So x is equal to negative sine of 60 degrees, which is still root 3 over 2. As for y, that's cosine of 60 degrees. That hasn't changed. So that's y over 1. So y is equal to cosine of 60, which is still a half. So the geometry changed a little bit. And so we end up getting t of 0, 1 is equal to the x is negative root 3 over 2 the y is 1 over 2. Sure. Sure, we could have used 30 degrees. It's going to be a problem in something slightly different, so I'll come back to address it. But for this particular question, there would not be a problem if you used, this as 30 and then did x is equal to cosine of 30 instead of sine of 60. That wouldn't be a problem. I'll come back to that idea a little bit later when we generalize it, but for a particular question like this, it wouldn't be wrong. We'd end up at the same thing. Could we have dropped the perpendicular and did this triangle instead? Is that what you're kind of saying? Yeah, there wouldn't necessarily be a problem with that. You'd end up in the exact same kind of idea. The x would still be the opposite side, and the y would still be the adjacent side. You'd still be fine if you did it that way. Right. In other words, the standard matrix is a half root 3 over 2 from column 1. Column 2 involved t of 0, 1, and we get our standard matrix T. Right. So any questions about how we found our standard matrix for this rotation? All right, so what if I didn't give you the specific angle 60 degrees or pi by 3? What if we did it in general? So what changes? How I filled the standard matrix. The first column is t of 1, 0. The second column of t is t of 0, 1. So that's the stuff we did in terms of how to use elementary things. So in general, for an angle theta, so for any angle theta, what would our standard matrix be? So did any of this, other than getting a half, did any of these ideas depend on the fact that the angle was 60? The angle was 45. Would we do the same thing? Yeah, absolutely. So in general, we get cosine theta, sine theta for t of 1, 0, negative sine theta, cos theta for 0, 1. So somebody mentioned before, and it wasn't wrong, but somebody mentioned before that could we have just taken this whole thing and used 30 degrees here instead of 60? The answer to that is yes, but if you did that, you'd end up with negative cosine of 90 degrees minus theta and sine of 90 degrees minus theta if you did that. So if you, for this specific example, yes, you could have taken the other angle instead of using 60 like we did. Using 30, you could do that, but that makes it a much uglier looking formula to use if you tried to generalize it. So it's not wrong, but it doesn't generalize like the method we did. Which is why I would recommend kind of not trying it from that direction. All right. So if you have any questions about that, let me know. If not, see if you can use that answer to see if you can determine what happens to the vector 1, 2 if you rotate it by pi by 3. So we actually just did the last question. So try the second last question. What happens to 1, 2 if you rotate it pi by 3? All right. So why don't we do the same thing? We already talked about how to take 1, 0 and 0, 1 and rotate it. It was just a messy trig calculation, but we got it done. So would the same ideas work here? Can we just kind of drop this perpendicular? I mean, the length is different, but I mean, we could find that out. The length of 1, 2, it shouldn't take you too long to realize that's root 5. This angle right here is 60 degrees, which means that our y is going to be, well, it's root 5 times something. Root 5 times which angle? Maybe it's sine, maybe it's cosine of what angle? 60 degrees? So that would be 120. Okay. So what's this angle or this? I don't care which one, but what would either of those angles be? Be 30? Would it be 30? Well, it can't both be 60 because it's a right angle triangle. They have to add up to 90. Yeah, this doesn't work anywhere close to as nicely as it did before, and we can debate on whether it was nicely before. Because it's not, this angle isn't the one that's 60. It goes here. We need to figure out this angle that we never had to figure out before. Have I confused you? Good, because we're not doing this. T of 1, 2, how can we find T of 1, 2 much more easily? Yeah, we have the standard matrix. Let's use it. And multiply it by 1, 2. The beautiful part about this, and for reflections, it didn't matter very much. For rotations, or for projections, it didn't matter very much. We can find those easily enough. But for rotations, it is a lot easier to rotate the standard vectors than it would be other vectors. Meaning that we create the standard matrix using the nice vectors, and then we can use it for the more complicated things. In other words, this is what, a half minus root 3, and root 3 over 2 plus 1. So T of 1, 2. So the vector 1, 2 goes to, the x-coordinate goes to a half minus root 3, and the y-coordinate goes to root 3 over 2 plus 1. So even though this works for all of our other operators, it's really the rotation operator where we can take advantage of the fact that everything kind of turns into matrix multiplication once we find that standard matrix. The way we would have had to have done it here is we first would have had to have found that vector, which is tan inverse of 2, add 60 degrees to it, and so this angle right here would be 90 or 180 minus 60 plus tan inverse of 2, and nobody wants to do that. We were rotating by the same angle. So we were rotating by the same angle, so we used the same standard matrix we already computed. If you change the angle, then we'd have to put the new angle into the standard matrix. But yeah, this, what we did here in general, that matrix could be used for any rotation. You just have to plug in the appropriate angle. So we're not going to go through this entire next example. I do have one more example I want to do on Thursday. The question kind of becomes, what happens if we make this three-dimensional? So I'll leave this up to you to see if you can give these here a try. But the idea behind how we would do it in 3 dimensions is we're not doing it in 3 dimensions. So the only rotation operators we're going to do in 3 dimensions is, all right, it might be in R3, but we're only going to rotate it in the XY plane. So in other words, the Z stays exactly the same. And you can look in the textbook, it's just sticks a standard matrix for you to look at. But in reality, our transformations in R3 is just the same standard matrix for X and Y and 0, 0, 1 for the Z. So we're not actually going to rotate some 3-dimensional rotation. So feel free to give that a try. We will do this example right here. So that's where we'll start with on Thursday, is kind of putting a few different transformations together. So I do have that one more example I want to do. But other than that, we are done chapter 4. Other than that one example we're going to do here. And then we'll start off with our final chapter, chapter 5. If you have any questions about any of this, let me know. If not, have yourselves a good day.